Good evening. Good evening. Hope all is well. Hope everyone's doing all right. All right. So we got two in here. So we didn't do anything last week. On Monday I had a little bit of an emergency, and then Wednesday, we didn't have class. I forgot what it's called, but one of you guys shot me that email, reminded me of that. So we didn't have class Wednesday. So if you didn't see anything from me last week's because we didn't do anything or record anything last week. So we have one more section to cover out of chapter 3. Then we'll be done with chapter 3. And so we'll just do that today and then go from there. So got a couple of problems that we are going to look at. So 3.8, it's related rates. All right, so water runs into a conical tank at a rate of 9 feet or 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Give you a chance to copy that down. All right, scrolling up some. So I did my best to draw this out. Of course, if I scroll it too far as the black is concerned, let me know. All right, so we want to know how fast is the water level rising when the water is 6 feet deep. All right, so here is the drawing. So basically what we're asking is right here in red, what is dy dt? What is y with respect to t when y is 6 feet? All right. So we want to know this water level right here rising. How fast did it rise? What's the rate of it rising to 6 feet? So over here, we have the explanation of certain things. V is your volume. It's in cubic feet of the water in the tank at time t minutes. X is the radius of the surface of the water at the time t. And Y is the depth of the water in the tank at time t. Oh, also, I didn't point out, let me scroll up. Once again, your rate is, how can I say it? Your rate is going to be a derivative. And here it says the water runs to a conical tank at a rate of 9 cubic feet per minute. So that is the rate, the total rate. So that's the derivative of the volume of the tank with respect to T. That's how much it's rising at. If you look at the tank, it tells us that our radius of our tank is 5 feet, and then the height, 10 feet. Now, if you're talking about X 6 feet deep, we have this smaller triangle down here, a smaller conical shape down here, where X would be the radius, and then Y would be the height. All right, somebody still copying? Can I scroll up? All right. So here we're just putting down general information. So I already mentioned that the derivative of T, derivative of V with respect to T, is 9 cubic feet per minute. Y is equal to 6 feet. And this is your general volume formula. And the radius is X for us. Oh, and the height is H. All right, so we can use similar triangles to solve for X. So here we use X and Y in a proportion because of similar triangles. And so we do X over 5 equal to 5 over 10. So let me go back, make sure we see that. So X and Y right here are related to 5 over 10. So that's how you can use similar triangles in this case. All right. So we substitute it into the volume formula for X. All right, y squared, y over 2 squared is y squared over 4. Still got y out here. So multiplying y to that would be y cubed over 4. And that 4 times 3 in the bottom would be 12. So this is what we have now. All right, any problems? Let's see what we're doing. All right, so now they tell us the best way to go is to find the derivative of V with respect to T. And all of this is connecting because let me go back here. Remember we said that what we're looking for is the derivative of Y with respect to T. And so that's why we substituted in X, because that we wrote X in terms of Y. And then also we have this relationship right here, derivative of V with respect to T. So we'll be able to set some things equal to each other in a second. So we find derivative of v with respect to t, and we're talking about this v right here. So we have to do it implicitly. So we take the derivative of y cubed, which is bring your 3 down, and then that'll give you y squared, subtract 1 from the 2. Then I can cancel out that 3 with that 3 and the 12, and that leaves me with just 4 in our denominator. And pi y squared. And remember, we're deriving this implicitly. We're taking derivative with respect to t, so it still has to be this piece here, dy dt. All right. All right. Try to scroll up. So now, remember, we want to find dy dt, but we have something that we can plug in for derivative of t, derivative of v with respect to t, and we have something we can plug in for y. And so that's what we got right here. We're going to use derivative of v with respect to t being 9 and y being 6. So we plug those values in. Now we can solve for dy dt. So 6 squared is 36. 4 can divide into 36 and leave us with 9 equal to 9 pi dy dt. Then we can divide both sides by 9 pi. Means dy dt is equal to 1 over pi. All right. That's going to be approximately 0.32. And in conclusion, the water will be rising at 0.32 feet per minute. Questions on that before we look at another one? So everything we were doing was trying to connect us to this final. Oh, Sam, my eraser on. Sorry about that. All right. Everything was trying to connect us to that dy dt. So we were doing things to manipulate the problem to get to dy dt. So let's look at another one. See if we can walk through that one. So we have a hot air balloon rising straight up from a level field. It's tracked by a rangefinder, 150 meters from liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? All right, let's scroll up. All right, try to draw my little balloon there. See if I can. Nah. All right, so that's my balloon. We got the rangefinder down here. And for most of these, if I'm not mistaken, I don't have my book out. Let me see if I have it still pulled up. I know they drew the cone. Yep, they drew the balloon. Yeah, so for the most part, they give you the drawings and they give you those relationships that I gave you. Yep, so yeah, they did the same thing with the cone. So you don't have to come up with all this stuff from scratch. Yep, they tell you. So, all right, so we have the derivative of pi with respect, not pi, theta with respect to t. There's a 0.14. You know that we got that from right here. And that's when theta is pi over 4. So we're talking about this angle right here. He said he's 150 meters from liftoff point. So that's showing that right there. And we know how fast the balloon rising. So that's why we had derivative of y with respect to t. Y is going up when theta is pi over 8, pi over 4, excuse me. All right. So scrolling up. So theta is the angle in radians that the rangefinder makes with the ground. So, looking up. So you're talking about looking up at the balloon. The height in meters of the balloon above the ground is going to be y. All right, scroll up. So in the purple, just reiterating what we said there. And it says next, we're going to use the trig function to establish our equation. All right. So if you go back to SOHCAHTOA, that's one way to remember the relationships. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent is opposite over adjacent. We're talking about the sides. All right, so the best look for us will be tangent. So let's go back, make sure we understand why. Our angle, theta is right here. The sides that's relevant to us is opposite and adjacent right here. Because we have 150, we're trying to find y, and we have 150. Using our hypotenuse wouldn't be to our benefit because we don't know what it is. So we take the side that we know, which is 150, that's adjacent to theta, and then we take the opposite side, the side that's opposite to theta, because that's what we're looking for. We're looking for y. So that's why we're going to use tangent. So right here, and if we solve it for y, I'm multiplying both sides by 150, well, y equal to 150 tangent theta. From there, we can find dy dt, take the derivative of y, which is 150 tangent theta, with respect to t. So that means, once again, we're deriving it implicitly, so we can't take the full derivative. Derivative of tan theta is secant squared theta, but then you're going to have this piece, d theta dt, because we're taking it with respect to t, not with respect to theta. Okay. So now we can substitute in theta and d theta dt. Let me know if I scroll up too far. All right, so plugging in pi over 4 for theta and then 0.14 for d theta dt. Secant squared, so power of 4 is the same thing, secant to power of 4 squared. So we can apply the secant to power of 4 and then square it. All right, so secant of power of 4 is just the square root of 2. Notice that square and square root will cancel, leaving you with just 2. 2 times 150 is 300. 300 times 0.14 is 42. Bloody okay. So the balloon is rising at 42 meters per minute. All right. Questions on that one before we look at least one more. All right. Very good. All right, so we have a police cruiser approaching a right angle intersection from the north. It's chasing a speeding car that has turned the corner. Write that word better. Turned the corner and is now moving straight east. All right, when the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance should be determined with radar that the distance between them and the car is increasing. Of course, if I scroll up too far, let me know. At 20 miles per hour. Says if the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Let's go look. It's my little diagram. It's supposed to be cars. So see the top one is the police. Bottom one is the cruiser. Well, no, the police is the cruiser. But whoever's the police is chasing. And you see our rates. And yeah, I believe that's -60. Let me make sure. Yeah. So there's a -60 since he's going down. All right, so we see in green, X is the position of the car at time T, Y is the position of police at time T, S is the distance between the car and police at time T. All right. And also notice 0.8, 0.6, X and Y. You scroll up. All right. So this time, and it's all about using formulas and using relationships that are a benefit to you trying to figure out what you're trying to figure out. So this time, if you go back and look at what we do have a distance here between these two cars. So the distance formula would be to our benefit to use, x squared equal to x squared plus y squared. Use it in that fashion. And also we solve it for s. That should look more familiar to you because most definitely give the distance formula with the square root of x squared plus y squared. Just have a d there. And we have your ordered pairs. 2 squared and so on. That should be minus. But anyway, that's the distance formula. So we can take the derivative of this with respect to t. So derivative of s with respect to t, and that'll connect us to this right here, just 20 miles per hour. So we'll take the derivative of this with respect to t. So bring down your 2 in front of s, subtract 1 from the exponent, but still left with ds dt. Derivative of x squared, bring down your 2, subtract 1 from your exponent, still left with dx dt. And then the same thing with y squared, 2y dy dt. So now we can solve for ds dt. Divide both sides by 2s. All right. Ooh. All right. So I don't know what just happened. I hit something and it changed something. Hopefully it didn't mess up anything that we're doing. I most definitely didn't mean to do that. Lost my pen. All right. So dividing by 2s both sides, the 2's cancel. And then I just brought this 1 over s out to the front. I wonder what did I hit? It didn't disappear just that quick. All right. Well, so that 1 over s, the s down the bottom, I just brought it out front. So that's how they got there. All right. Then I substitute in for s, and that goes back to what we did, this relationship, just to get rid of s. On the right side. So we have 1 over the square root of x squared plus y squared times x times dx dt plus y times dy dt. And now we can substitute in all values that we know. And then let's go back real quick. Remember what we were looking for was dx dt. So all the pieces that we're plugging in for now leaves me with just the dx dt that I don't know. All right. So let's go ahead and multiply the stuff out. All right. So I went ahead and multiplied this. 0.6 times negative 60 is 36. Went ahead and multiplied this to both sides to get it out of the denominator. Squared 0.8 and 0.6. It gives you 0.64 plus 0.36. Adding those together ends up being 1. So they ended up simplifying for us anyway. Square root of 1 is 1. So that leaves us with just 20 on the left. All right. Any problems? Any problems? Still solving. So we're adding 36 to both sides. So now we're looking at 56 equal to 0.8 dx dt. Divide by this 0.8. 0.8 cancels. 56 divided by 0.8 is 70. And that's the answer. So the car speed was 70 miles per hour. Questions on anything. Some of the stuff, you might not have questions till you get in there, try the stuff out. Some of the stuff, may be new to you, so you might give yourself a chance to digest it. And that's understandable as well. So this is our last section in chapter 3. So next class will be open for you guys to ask whatever questions you want, bring any questions that you have to the table. And, we'll try to walk through them, make sure you're good to go before we head into the weekend. All right, and then we'll also talk about, let's see, this is week 6 or 7. So this is week 7. So next week, midterm should be due after next week. So yeah, we'll talk about that and everything. Next class as far as the due dates on chapters 2 and 3 and stuff. So any questions, concerns, or comments before we close out today? Anybody? Okay. All right, so next class, review day, questions if you have them. And outside of that, we'll figure out where we're gonna go from there. All right, so you guys have a good one, be safe, and I'll see you next class.